All right, let's take a look at today's lesson. So today we're going to be doing the first day of graphing polar equations. And I've split the polar equations into two kind of groups. Today we're going to look at these two types, main types. This where we have circles that are generated by this equation. And then these type where, they have names, limicon, cardioid. You don't have to memorize the names. That's not going to be on an assessment or anything, but I think it's interesting. These are the types that we're going to be working with today in this format. And then we have some more types that we're going to be working with tomorrow. So I split that in half. So let's take a look at this first type. These actually are circles. If you don't have to memorize this form, but some students like to have an idea of what they're going to be graphing before they graph it. So this type you would have like r equals some number cosine theta. This number represents the 2 and the a. A really represents the radius of the circle. You could know what you're graphing before you ever graphed it if you memorize that. I'm not asking you to memorize it. I'm just saying that certainly is an option for you. So they're going to be just a variety, depending on what our radius is, a variety of different circles that would be symmetric around the pole, this polar axis right here, if it's cosine. If it's sine, then we're still going to have circles, but they're going to have a different orientation. They're not going to be in that location. They're actually going to be, up here around the y-axis. Kind of makes sense. Cosines around the x-axis, sines around the y-axis. So we'll be looking at those today. Then we're also going to look at that polar curves in this form, like a number plus or minus another number with a cosine, or a number plus or minus another number with sine. Okay, that format. So let's look at those. You can. This is the way that the equations work. Again, you don't have to memorize it. I'm just talking about how it's formed. So A would be this number, that's the one out here, the add or subtract, and B would be the coefficient of the trig function, sine or cosine. If you were to divide those and you got a number less than 1, then it would create this little guy with the inner loop, the limicon with an inner loop in it. That's what it would create. You would know before you ever graphed what what you would be graphing. Here, if you were to divide these numbers, A and B, and get 1, it would create a cardioid that basically just comes to a point. It doesn't loop inside like this one. It just comes to a point and then goes back out. If you were to divide these two numbers, A and B, and you got a number somewhere between 1 and 2, it would come in, but it wouldn't come in at a sharp point like this one does. It would come in just, gradually and then go back out. And then if you divided these two numbers and got a number that's larger than or equal to 2, it would kind of look like a circle or an ellipse is what it would look like. That's what it would look like. And again, if sine was in the equation, it would produce a similar shape to this, but it would just be oriented differently.
Is that last one asymmetrical?
They're still symmetrical, but it depends on what it's symmetrical about. This one would be symmetrical about the pole here, but it's kind of elongated. Yeah, oh, I see what you're saying. Yes, it's a little fatter right here, and it's a little shallower right there. Yeah. Okay. So these are the kinds that we're going to look at today. Are there any questions about those? Any other questions? Okay, let's go to our examples on the next page. Now there are a couple of different ways. Actually, I can think of 3 different ways to graph these. Some students, I know you're going to find this shocking, some students just want to memorize the formulas and plot some points. That's what they want to do. They just want to plot a few points, memorize the formula, and know what it is. That's fine. You can do that. Some students just want to memorize the formulas and go from there. And then some students just want to plot points. So we got a lot of different variation. What I like to do is I have a lot of formulas that I have memorized. I don't want to make any room for any more. So what I do is I do a Cartesian graph, and I just use that as my t-chart. Instead of doing a t-chart with random points, I do a Cartesian graph. Okay, that's how I'm going to teach you. You can certainly graph them however you want to, but that's how I would typically do it. So I know you're probably excited. You're like, oh, I miss graphing trig equations so much. Yes, today we're going to be looking at that again. Now, if you recall when we were doing that, last semester, they got kind of crazy. They had like 4 transformations, and then even sometimes they're flipped over an axis. These are going to be pretty simple. Maybe you're going to have an increased amplitude. Maybe you're going to have a shift, a sinusoidal axis shift. They're not going to be real crazy to graph. They're pretty straightforward. So that's what we're going to do. So I'm going to do the Cartesian graph of 4 sine, and I'm going to use that as my t-chart to plot this curve. All right. So we know this is our amplitude, which means it would go up 4 and down 4, and there is no vertical shift, so it's at the x-axis. I'm going to use my regular, 4 locations that I always use, pi over 2, pi, 3 pi over 2, and 2 pi. This in Cartesian coordinate world has a period of 2 pi. That does not mean it's going to have the same period in polar world, but we'll look at that. Okay, so recall sine starts at the sinusoidal axis, and then it goes up and then down. So it goes like that. And now this is what I'm going to use to plot my graph. I'm going to use this x-axis. Instead of as an x, I'm going to use it as theta. And I'm going to use this y-axis. Instead of as y, I'm going to use it as r. And I'm just going to I have an infinite number of points that I can plot now if I wanted to. That's what I'm going to do. So at an angle measure of 0, my r measure of 0, so I would actually start here at the pole. At an angle measure of pi over 2, I'm at 4. So here's my angle measure of pi over 2. I'm at 4. 1, 2, 3, 4. And now we talked yesterday that it's quite rare that there's a straight line in a polar graph. We would not connect this straight line like that. So how do we do this? Well, it's going to be curved. So let's look. So this is the first quadrant between 0 and pi over 2. This is what's happening in the first quadrant. As you can see, as I go to at pi over 4, I'm maybe, I don't know, it looks like about 3.5 or more. So at pi over 4, 1, 2, 3, I would need to be kind of, out here a little bit, kind of plump. If you want to do another point, you can. You don't have to. We want to make sure that these are nice and filled out. We don't want to make them skinny. And let's just explain why. So what we're doing is we're prepping for next year. And next year, we're going to be finding areas of portions of polar curves, and we'll be intersecting polar curves. And so, if our graphs are narrow, it's going to look like they don't intersect at all. So we just kind of want to make them full. Just make them full. Think about, kind of exaggerate it, make it a little fuller than you think it would be. I tend to make them small too, so I have to really think about it and try to make them a bit fuller. All right, so that we're at pi over 2 at 4. Now at pi, we're back at 0. So what's happening in the second quadrant between pi over 2 and pi? Well, my r values are decreasing. I'm getting to an r value of 3, r value of 2, r value of 1, and then an r value of 0. So as I'm traveling through this quadrant, my r values are shrinking. And it's something like that. It's supposed to be a circle. Mine isn't a circle. If I was doing this on my paper, I would probably be compelled to erase it and redo it. But that's basically what it is. We have a circle here. And that's our very first polar graph. And so the format we looked at on the other slide, we saw that the format of 2a cosine theta develops circles all along here of different radius, right? So if this is 4, that means A would be 2. So that means this circle would have a radius of 2, which it does. Does that make sense? If you're wanting to graph by the formula, that's what you would look at. That's what you would do. Okay. All right, let's go to our next one. This one is 3 plus 3 sine. All right, so our sinusoidal axis has been shifted up 3 spaces. So 1, 2, 3. Our amplitude is 3, so we would be up 3 and down 3. We're still going to do our same points, pi over 2, pi, 3 pi over 2, and 2 pi. And sine starts at the sinusoidal axis and then goes up and then down. So it looks like this. Okay. So I want to pause on this for just a second, and I want to make a special note about number 1 and the period. Notice how I'm graphing the Cartesian period. The Cartesian period does not necessarily correlate with the polar period. Sometimes it does, and sometimes it doesn't. In this case, my Cartesian period is 2 pi, but I was able to complete this graph in just half of that in pi. So if I kept going, what would happen? At 3 pi over 2, I'm at negative 4. So at the angle measure 3 pi over 2, I'm at negative 4. Where would that put me? Over here, right? We're just basically retracing my circle again. So in this case, this period, the Cartesian period was 2 pi, but the polar period was pi. It was different. Now let's investigate this one. The Cartesian period is 2 pi. Let's see what the polar period is. What do we get from the polar period? All right, so at angle measure, so this is my thetas and these are my r's. So at angle measure 0, I'm at 3, so I'm here. At angle measure pi over 2, I am at 6. Okay, and we're going to connect these with a nice, plump curve. We want to kind of exaggerate. Is everybody okay with that? Okay, at angle measure pi, we are at 3 here. Again, we're going to connect that with a nice full curve. In the third quadrant between pi and 3 pi over 2, so we're in the third quadrant, we're actually going to hit 0. Okay, so hopefully we understand this isn't going to be straight across, right? So what's happening here? My r value is going from a 3 to a 2 to a 1 to a 0. So it's basically going like this. Then from 3 pi over 2 to 2 pi, I'm back to 3. And I've completed my graph. That's a cardioid. Now in this case, the Cartesian period happens to match the polar period, right? It took me all of this, 2 pi, to be able to complete this graph. So they don't match perfectly. I just want to make sure that you're aware of that, and it's okay. Okay, and there's our graph. So if you're going by the formula, if you recall, this is A and this is B. When I divide A and B and get a 1, I get a cardioid, which is what we got, where it comes in at a point and comes back out. Okay. The last one that we're going to do, this one right here, again, A is 2 and B is 4. When I divide A and B and I get a number less than 1, what's going to happen? I'm going to have the inner loop. So I just need to, it would be kind of good to know that you're going to have the inner loop, right? I mean, it'd be kind of good to know before you start. So let's draw this Cartesian graph. I'm going to put it down here. Let's see, we've been shifted up to, so our sinusoidal axis is up to, and then our amplitude is 4. 2, so 1, 2, 3, 4. 1, 2, 3, 4. We're still going to use the same locations, pi over 2, pi, 3 pi over 2, and 2 pi. And cosine, if you recall, cosine starts at its maximum value, right? It starts up and then goes down to its minimum value and then goes back up. Okay. Alright, so let's see what we got going on. So at angle measure, so this is my theta and this is my r. At angle measure 0, I am at 1, 2, 3, 4, 5, 6. I'm at 6. Right here. Okay. At angle measure pi over 2, I am at 2. So again, we're going to kind of exaggerate, make it nice and plump. Notice what's happening here. So this is their significant between pi over 2 and pi. These are second quadrant angles right in here. But notice what happens. We're going to cross the polar axis. R is 0, and then we're going to go negative. If my angle measure is in the second quadrant, but my r is negative, what quadrant am I actually going to be in? If my angle measure is up here in the second quadrant and I have a negative r, it's going to push me over here, isn't it? Okay, so we need to keep that in mind. This one is a little bit more difficult to graph than the other ones because this is not at one of my pi over 2, pi, 3 pi over 2, 2 pi. It's not at a nice even place where we cross the polar axis. The r is 0. So what's going to happen is I'm going to be in the second quadrant for just a little while, which is right here. I'm in the second quadrant for just a little while. Here, right here is where I cross through the pole. This corresponds with this. Then I am supposed to be all the way to pi. I am supposed to be not actually in the second quadrant, but over here. You with me? And the value at pi is negative 2. So pi is negative 2. It's right here. So you kind of see what's happening? It's going to push me. So I am negative r. I'm in the third quadrant. And then I am at a negative 2. So I'm going to pause here for a second. Okay. Probably the ones with the inner loops, are probably the most difficult to draw. And what we need to be cautious about is that we actually have to go through the pole. We have to show the graph going through the pole. Okay? Alright, so I'm at pi. So at 3 pi over 2, I'm back to 2. So how in the world am I going to get here? Yep, so what's happening? So my angle measure is in the, let's see, we're in the third quadrant between, where are we? Between, we're here, 3 over 2 here. Between pi and 3 pi over 2, so we're in the third quadrant, and our angle measure is negative, so I should be graphing up here, right? So that's this part right here. Then I have positive r's right here. I'm going to go through the pole, and I'm actually inside the third quadrant for just a little bit. Just this little part right here. So I'm going to pause here for a second. Are we okay? Lastly, in this fourth quadrant, all my r values are positive, so I'm going to actually be in the fourth quadrant the whole time. So I'm just going to complete, and I end back at 6. Okay. So with this kind, some students may want to just memorize that, if I divide these and get a number less than 1, it's going to be an inside loop, and plot their points and draw the curve. That's fine. I don't have a problem with that. You don't have to draw it exactly like I'm drawing it. I just want you to understand how it's happening. So the other thing that we're going to be required to do, well, in calculus, we would be asked to find the area of this inner circle, this inner curve. It's not actually a circle. It's just a curve. So we would need to know when the curve starts and when the curve stops. That's going to be significant for us. So and we need to know this, the curve starts and stops when r equals 0. That's when it does. You should write that down. The curve starts and stops when r equals 0. That's how I know. Unfortunately for us, it's not one of these points, pi over 2, pi, 3 pi over 2, 2 pi. It's not. It's here and here. We don't know what that is off of our Cartesian graph. So what are we going to have to do? Well, we're going to have to substitute a 0 in for r, and we're going to have to solve it. And at this time you're thinking, oh, thank you so much for having us solve trig equations this whole year. I don't have to remember how to do this, right? I already know I've been doing it. This is a really simple one compared to what we've been doing. So I'm going to substitute a 0 in for r, 2 plus 4 cosine theta, and I'm going to find out, so my goal is to find out exactly what these two values are. That's what I need to know. This is when my inner curve starts, and this is when my inner curve stops. Okay? So let's do that. So I move the 2 over, divide by 4, I get what? Negative 1/2 is cosine. So let's think about our unit circle. Let's see, cosine is negative in the second and third quadrant. Cosine would be 1/2 when it was tall like that. Let's see, 1, 2, 3, 4 pi over 6 or 2 pi over 3. That's my start at 2 pi over 3. It's 1, 2, 3, 4, 5, 6, 7, 8 pi over 6, which would be 4 pi over 3 is my end. So this is the start and stop of the inner circle, so that we would be allowed to find the area. Okay? All right. So how are we with this? Are there any questions for me?